Okay, so I had closed with a discussion of matrix multiplication, and I had pointed out that if you have two matrices, okay, A m n and B is of the order or dimension n into k. So the m is the number of rows, n is the number of columns. The number of columns in A and the number of rows in B must match. So am, B should be nk, and the order will be therefore m and k. These two k's cancel out. It will be row m, column k. Okay. Okay. Now, uh, matrix multiplication may appear to be somewhat similar to scalar multiplication, but there are differences. Matrix multiplication has some idiosyncrasies, as a result of which there are differences in scalar and matrix multiplication. If I multiply, for instance, 4 into 3, see, yeah, then I get 12. I will get the same result if I reverse the order. So AB is equal to BA. So this holds in the case of scalar multiplication, but in the case of matrix multiplication, will this hold? Look at this. What is the dimension of this matrix?
3 into 3.
And B?
So 3 into 2. Into 2.
এক্সকিউজ মি স্যার
হ্যাঁ,
স্যার আপনি কি অ্যাটেন্ডেন্সটা নিয়ে নিয়েছেন?
না,
আচ্ছা
আচ্ছা, sorry. Sorry. So this is 3 into 3, and B is 3 into 2. So as I've told you, these two are matching. Therefore, A33, B32. So in this case, multiplication is possible. But look at this matrix. What is the order?
3 into 2.
And this is B is
3 into 3.
okay. So now it is not matching. So multiplication is not possible in this case. But if you look at the matrix, this is A, this is A, right? I mean, what we had simply done was this. This is AB, I'm writing BA. That is what I've done. So the first problem in this rule, AB equal to BA, maybe if AB is possible, it does not imply that BA is possible. Secondly, even if it is possible, okay, let's take a very small example. 1, 2, 4, 2. Okay, what is A into B? Some of you find it out and some of you find out the opposite. See, over here, matrix multiplication is possible because it's a 2 into 2 matrix. Both are 2 into 2 matrices. tell me when you're finished.
So I guess the second one is -1, -2, 6, 6.
-1,
-2, 6, 6.
and this one has someone found it.
So I guess that should be -3, 2, 0, 2.
So that one is -3 or +3?
Sir, I think that one will be plus
I
3.
think it's +3.
Okay.
Yes, it should be +3.
So you can see that in this case, the matrix is of the same order. So AB into and BA both are possible, but we are getting different results. AB is not equal to BA. So even if the reverse multiplication is possible, we may not, in general, we will not get the same result. Now AB equal to 0 implies either A or B is 0. Very easy, just do this multiplication and see what we get. Some of you do this into this into this, first row, and some to the second row.
So the first one is 0, 0, 0, 0.
So we
It's
get
its identity matrix.
It's null matrix.
it's a null matrix.
Yes, a null matrix. Sorry.
But if you look at it, none of the elements are 0. Okay, so but in case of a scalar, suppose A into 4 is equal to 0. What does it imply about A?
A equal to
A
0.
must be equal to 0. But here we can see that neither A nor B are 0. They don't have a single matrix element which is 0. But still the multiplication is giving us 0. Okay, this I'll show you that CD is equal to CE. Okay, so let us see. We are multiplying a matrix by a scalar. And we are multiplying another, sorry, this is a, let us say that this is a scalar. And we are multiplying another scalar by alpha. Okay, and it is same. So what is the relation between A and B? They will have to be equal. Okay, so let us say 3 into 4. What will be this? This will have to be 4 also. But if you look at C, D, and E over here, these three matrices, and you can check that here CD and CE, if you find it out, it will be identical. But C, D, and E are all three completely different matrices. Okay, so these are three rules which normally hold in case of scalar multiplication, scalar operations. But if you try to apply them to matrix multiplication, then none of these three rules will hold. Okay, is it clear? You will see over here that CD is equal to CE, but as you can see, D and E are not equal. Okay. Now we turn to different types of matrices. One is an identity matrix. So this is a matrix which looks like when all the diagonal elements are 0. So let us say it's a 4 into 4 matrix. So A11, A22, A33, and finally A44. This element is 1, all the other elements are 0. We often write this as in this way. Okay. So this is the matrix equivalent of 1. Why it is is it the matrix equivalent of 1? Because if we multiply, use the identity matrix in multiplication, then we are going to get the original matrix. So A into I will be I into B will be B. Now note one important fact that when we are writing this N and N are matching. I is always square. Here N and N are matching. So we have to write this a bit carefully. If I take, for instance, what is this equal to?
Sir,
Hmm?
so could you explain that part? A M into N I N equals to A. No, sir. Like I got it, no, sir.
That is the definition of an identity matrix.
Oh, yes, sir.
A into I is equal to A.
Yes, sir,
IB
got
is
it.
equal to B.
Oh, yes, sir, got it, sir, got it, sir.
What I'm saying is you have to be a bit careful about a dimension. For instance, over here,
See, here
what?
the multiplication is not
Sir,
possible
multiply.
because
It won't multiply.
Yeah. See, this is basically square matrix, so it's K into K, N and K, not matching. So multiplication is not feasible. Okay. Now, if you have a square matrix, then you can take the infinite power. So in that case, you can multiply this by the original matrix. A into A, that will give you A square. You can multiply A square by A, you will get A cube. You can multiply A cube by again by A, you will get A4. See what is happening because of the square. See, AMN, sorry, it's, I'll make it AM. What will be A square? The dimension of A square.
M into M.
This into this. Right. So I can multiply this by again by A, which is M into M. Okay, so the dimension doesn't change. It is always M into M. So I can continue to multiply this by A, and I'll get, depending on what the value of N is, it will be A. If N is 2, it will be A into A. If it is A cube, A squared into A, like this. Now, if A square is equal to A, then A is said to be an idempotent matrix. If A is idempotent, in fact, you can generalize this. An will always be equal to A. Whatever power you take, you will always get the original matrix.
Sir, n can be any value.
n can be any value.
Acha.
Ne- Next is transposed. Consider a m into n matrix. So this is a how many m into n matrix. Okay, the transpose will be rows will be converted to columns. So the first row is converted to the first column. The second row is converted to the second column, and so on. So if A is m into n, it will become, the transpose will be n into m. Okay. And the diagonal you can see, let's see, this is A11. So the diagonal elements will remain same. But look at A12. What does it become over here?
A to 1.
A21. So the ij changes. Sorry, I made a mistake over here. It should be ji. Okay. Okay. Now there are certain rules of transpose operations that if you take a double transpose, you get back the original matrix. Then, if you add two matrices and take the transpose, is the same as taking the transpose first and then adding them. This is scalar multiplication. You're multiplying a matrix by a scalar and then taking transposed. You can simply multiply the transpose by the scalar. And AB, sorry, it should be single prime, is equal to B prime into A prime. Oh, yeah. Sorry. Achha. Next, we come to what I call symmetric matrices. Do you think that this is a symmetric matrix?
Yes, sir.
Yes, sir.
Why?
If you take the transpose, then it
So because the
remains the same.
diagonals has 1.
The transpose will be equal to it.
This?
No, sir.
Okay. Take the transpose. Right?
So the transpose should be equal.
So is it equal?
Yes, sir.
Yes, sir.
Okay. So actually what we require is Aij.
Equal to AGI.
Yeah, but now this is important. When I is not equal to j. Okay, so symmetricity, when we're looking at whether the matrix is symmetric or not, we have to look at the non-diagonal elements. Not the diagonal elements. They can be different. They can vary. The reason is that A11 will always be equal to A transport 11. Right? That is why we don't need to worry about the diagonal elements. It is only the off diagonal elements that we have to ensure. Okay. Inverse of a matrix. So A is equal to I, or see, both are possible because I is a square matrix. Okay, so that means A is also a square matrix. Okay. Sorry, I made a mistake over here. Okay, so BA is equal to I. We post multiply by A inverse. So it is B. Now this part is I. B into I is B, and I into this is A inverse. So B is equal to A inverse. Okay. So suppose we have a linear equation system which is given by Ax equal to B. Now, if we pre-multiply by A inverse, we are going to get this. Or this is I, and this will give us some matrix which we call C. Or X is equal to C, right? So that means if I have a linear equation system like this, A11 x1 plus A12 x2 let us say it's a square system.
So,
Yes,
so I guess out there, so it should be AN2. And so in the
this one, this
second
one.
line, it should be B2.
Yeah, this is B2. Yes, you're right. Okay, so we can write this as Ax equal to B when A is this matrix, the coefficient matrix. Okay, X is the variables and B is,
The constants on the right hand side.
sorry, it should be N. So we simply have to multiply, find out the inverse of A and multiply A inverse into B. So what we are going to get is two column vectors x1 to xn, and so now we can simply match them. X1 is equal to C1 and so on. Xn equal to C. Okay, now over here A inverse is unique. Therefore, A inverse, if A inverse is unique, then C will also become unique, which means that we are going to have only one set of one vector C, which is the solution set of this equation system. So in this way, Is it possible if I give you an equation system Ax equal to b, is it possible to solve all these equation systems?
Yes, sir.
Okay. This one, or will I write it down?
Sir, here M is not equal to N, so the A is not a square matrix. Then A inverse will not exist.
So A is not a square matrix. Therefore, what will the inverse will not exist. So that means a necessary condition is M should equal to N. It is a square matrix. Okay. Now tell me, what is the meaning of M and what is the meaning of N? What does M tell us?
I guess rows.
Rows in the matrix, of course, but in the equation system,
Number of equations.
and N,
Variables.
so what we are seeing basically is the number of equations and number of variables should exactly match. This is called an exactly identified system. Suppose M is greater than N. What does it mean? If M is greater than N, what does it mean?
Number of equations are greater than the variable.
So here we have additional. Oh God, what I've written. We have additional extra equations. This is called an over-identified system. And finally, if M is less than N, we have too few equations. This is called an under-identified system. This is simply not solvable. We won't get a solution. Over here, what happens is unique solution is not possible. Only in this case. Do we get a unique solution? Okay, so having too many equations is also bad. If we have too few, well, we can't solve it. We just have to go back home. So if I give you a under-identified system, it will be, you should be very happy, because in that case, I can't expect you to solve it. But if it is over identified, yeah, you can solve it. The problem is that you need not have a unique, you will not have a unique solution. You will have multiple solutions. And well, we don't know how to choose between these multiple solutions.
Can you please show the last slide? Okay, sir, done.
I want to add something to it. Okay, so the necessary condition is that A has to be a square matrix. Number of equations equal to number of variables, and it is so that we get a exactly identified system. But even if A is a square matrix, will we get A inverse? Does it exist? And the answer is no. Even if you get A inverse, I mean, if you get a square matrix, it is quite possible that A inverse will not exist. Okay. Now I'm going back to the earlier slide. See, over here, we have seen that the matrix multiplication is not matching with scalar multiplication. Look at this matrix very carefully. Look at the first row and look at the second row. Can you tell me what is odd about the A matrix?
So the first row is 2 into the second row.
Yes. And compare the columns of the second row.
Then it is 2 into the first column, the second column.
-2.
Yes.
Look at C and D. Compare the rows.
So
So it is 3 into the
thrice.
First is 3 into, and the other is 2. D te নেই কিন্তু D তে কোনো problem নেই.
Yes, sir.
So what we are seeing is that you have an equation. See, this is an equation, right? Or this is a row, or this is a column. Instead of getting a completely fresh row or fresh column, I'm simply transforming the column, multiplying this by a scalar, and then I'm repeating the earlier column. Okay. This is called what we call a case of linear combination or linear dependence. Sorry, এইটা আমার ভুল হয়েছে। No, it was ঠিকই ছিল। Okay, so we have three columns, C1, C2, C3. What is C3?
C1 plus 2C2.
So we see that C3 is a linear combination of C1 and C2. Okay, if you want to generalize this, a particular column, let us say N, okay, when alpha I is so what we are saying is some of the alphas can be positive, some of the alphas can be negative, and it is also possible that some of the alpha is 0. For instance, if we take this case, let us say 4, 2, and 3, and let us take another 2, 1, 0. Okay, what is C4? Let us suppose alpha 1 is 1, that is positive. Let us suppose alpha 2 is -2, that is negative, and alpha 3 is 0. So what is C4? C4 is basically C1 minus C2, right? So we get 2, this is 1, and this is 3, right? So even though we write it in this way, some of the alphas can be 0 also. So C3 does not have to be, a particular Cn does not have to be dependent on all the rows, all the columns, sorry. And I'm writing this in terms of columns, but such linear combinations can also be for rows also. So maybe R2 is okay. It need not be the last or first also. It can be someone which is in the middle also. This is also possible. So if a row or column is a linear combination of the other rows or columns, we see that it is linear dependence. Okay. If you have linear dependence, then the problem is A inverse will not exist. Therefore, the system cannot be solved even if it is exactly identified. Is it clear?
Yes, sir.
So if you are given a system Ax equal to B, what you simply have to do is the first step is look at the dimension of A. If it is not square, you have to stop. You can't solve the equation. And if it is a square matrix, then you go to step 2. And then you have to ascertain whether there is any linear dependence in rows or column. Now the problem is the first step is easy. You can just look at the M and M and know whether it's a square or not. But this step is not very easy. I mean, I've given you problems which are very easy to understand, very easy to identify. But in many cases, you'll find, particularly if you have got a very large dimension, 10 or 12 equations. In such cases, it becomes very difficult to identify whether there's linear dependence or not. Because remember that you don't know. See, in the earlier cases, I was telling you, look at the row, look at the columns, compare the rows, compare the columns. And secondly, it was only a 2 into 2 matrix. But if you don't know what to look at, whether to compare rows and columns, and you don't know which row is a linear combination of which of the other rows, it becomes very difficult to ascertain whether there is any linear dependence or not. So theoretically, it's very easy to find out whether there is an equation system is solvable or not. But in reality, it's not that easy. Okay. Now the question is that fine, linear dependence means that we can't solve. But then the question is, why does linear dependence create a problem? So let us say that this is X, and you can see that R2 or rather R1 is 2 into R2. Okay, now look at the first equation. It is 10x2 plus 4x2 is equal to d1. Right? This is the first equation. Now, what is the second equation? It is simply half of this. Right? So what should it be equal to?
Half of D1.
D1.
Okay, so for simplicity, let me just reverse this. So two d2 is equal to d1. Okay, it's the same thing. আচ্ছা sorry আচ্ছা now how many variables are there in this system?
The two variables.
How many equations are there in the system?
One.
Because see, the second equation is virtually the first equation. I've just rewritten it in a different way.
Yes, sir. These are same one only.
So what I'm getting is an under-identified system. M is less than N. So A is not a square matrix. Right? And therefore A inverse will not exist.
Sir,
Huh.
sir, I'm telling sir, can we tell in this manner, sir? If we take in the matrix 10 4 5 2, sir, if we take 2 as common, then we are getting the two rows as same. So basically the value of the determinant is 0. So for finding the inverse, we need to calculate by 1 by determinant into that one. That's why sir 1 by 0, so it doesn't exist. Can we tell in this manner also?
আমি তো ডিটারমিনেন্ট ইন্ট্রোডিউস করিনি
Acha sir, okay, then by this manner, okay sir. Okay sir.
now I can argue if I say if I rule this out 2d2 equal to d1 this is not true or if I write it if I use this one d2 is not half of d1 ঠিক আছে in that case equation 1 and 2 are not same right I'm just giving an example what is the first equation 10x1 plus 4x2 let us say it is equal to 5 আচ্ছা let us say it is equal to 8 আচ্ছা এইটা হচ্ছে কত 5 this is 5x1 plus 2x2 in the first case we had assumed that this is half this is case 1 so that means equation 1 and 2 are basically same right now
Yes
let
sir.
us assume that 5x1 plus 2x2 is equal to 7 this is case 2 in that case equation 1 and 2 are not the same right so the problem that I was saying that you have an under identified system is not true in this case the
Yes
number
sir.
of equations is now 2 which is equal to number of variables okay Achha. Okay so now what I do is I might multiply this by 2 what do I get? 10x1 plus 4x2, right? Left hand side. Now this is equal to what? This was equal to 7. So if I multiply by 2, I have to multiply both sides. Now this becomes 14. Okay, so now I've got two equations. The first equation says 10x2 plus 4x2 is equal to 8. The second equation says 10x1 plus 4x2 is equal to 14. Is it possible?
Sir, can you ask the question once more? The last question.
See, what I've done was, I'm writing this in a general term. See, the first equation was 10x1 plus 5x2 is equal to d1. And remember that half of d1 is not equal to d2. Okay, I've ruled this out.
Okay, sir.
So what I do is I divide by 2. Both sides, obviously. So what does it become? 5x1. No, I've written, sorry, there's an error over here. This will be 4, right?
Yes, sir. 4.
This will be 2x2. And what is this?
Sir, half D1.
Now, this, yeah, sorry, half of d1.
D1, sir.
But I'm getting from this equation system, it is also equal to d2.
Ha, D2, sir.
Okay, so I had stated that half of d1 is not equal to d2. But over here, I'm getting half of d1 is equal to d2. So there's a problem of consistency. There's a contradiction. So either, I mean, this cannot be true, right? So therefore, I mean, this is following from the basic principles of mathematics, right? There's no error over here. So the error must be in this assumption. So that means I'm coming back to case 1. So I've got two situations. Either I get an under-identified system or I get a system which is simply not consistent. So that means if I get a matrix, if the A matrix is linearly dependent, then this is going to result in either of these two problems. It will be either inconsistent or it is going to be overdetermined, underdetermined, sorry.
The difference কি দুটোর মধ্যে স্যার? Inconsistent আর underdetermined.
Underdetermined hole, there's no, as such, there's no contradiction. I simply can't solve it because I have too
আচ্ছা,
few equations.
okay.
And inconsistent means what I'm saying, I'm making some statements, all the statements cannot be true.
আচ্ছা স্যার।
Now let me come to the concept of a rank. You have finished this? May I wrap it off? So let A be a m into n rectangular matrix. Okay, so I'm not talking about square. It can be a rectangle also. Okay, so let us see that, as I've told you, that I've got m rows and I've got n columns. Okay, now out of the m rows, I find that m1 are linearly independent. So what is the relation between m and m1?
So I guess it not equal to.
Sir, M1 less than M?
m1 less than n. Can it be equal? It can also be equal. আমার সবকটা, all the rows can be linearly independent. Look at this row matrix. Okay, so I'm taking the double of this. Are they linearly independent or dependent? Look at the rows. Are they linearly? Can I express R1 as a linear combination of these two? Or R2 as a linear combination of the other two? No. এখানে কোনো, there's none of the rows are linearly dependent. So M is the number of rows, and here all the rows are linearly dependent. Okay, let's just make this. Let me change this to 9. Now look at the columns. How many columns do I have? I've got n number of columns. Okay. Now out of the n columns, are all the columns linearly independent? Sorry, I made a mistake over here. এখানে independent হবে. Now let me write it out properly. Okay. So I've got 3 columns over here. But compare 1 and 3. আমি কি পাচ্ছি
The
এখানে?
second column is 3 into 1 column, first column.
Right. And C3, it is not connected with either C1 or C2. So that means I have got basically how many? There are only 2 columns. That are linearly independent. So n1 is equal to 2, which is less than n. Okay. So what is the rank? Sorry, what did you say?
So I told yes, sir.
Okay. Achha. Now the rank is the minimum of this. Okay, so here the rank is 2. So I have worked with a I've worked with a square matrix over here, but let us see what happens if we use a rectangular matrix. Okay. Have you copied it down? Is it clear?
Yes, sir.
Okay. So let us take let us take 4 rows. Okay. 1, 2, 0, 1. Okay. আচ্ছা এখানে দেখো এখানে কিন্তু একটা linear dependence is being created. So we have to remove this. Okay, in fact, we don't need so many. Look at this system. What is wrong with this? Is the systems, can we solve this system?
No, sir. A is not a square matrix.
So the system is over identified, right?
Yes, sir. First two rows are having linear dependence.
Wait. If I look at the system as such, it is over identified. The equation is 4, which is greater than number of variable, which is 3. So we are not going to get a consistent and unique solution set. Okay. The problem in this case, however, is solved trivially. As you have said, R2 is equal to 2R1. Okay, so that means the second equation is basically you're just rewriting the first equation. It's a dummy. So what you can do is you can strike out any of these equations. I mean, if you look at the linear dependence, I've got m rows, m equal to 4 rows, but only 3 rows are linearly independent. So m1 is equal to 3. And I've got 3 columns, all of which are linearly independent. So that means n is equal to n1 equal to 3. So what will be the rank of the matrix? Ra, it is the minimum of m1 and n1. It's matching over here, it is 3. So basically what it means is that although I've got a 4 into 3 matrix, we can easily drop one equation. We can easily drop either the first or second equation, in which case it becomes transformed into a 3 into 3 matrix. I'm calling this
Sir,
is. Huh.
Sir, if we drop any of the two equations, that is either the first one or the second one, sir, as you have written, sir, R2 is equal to 2 into R1, so won't
Sorry,
there be any...
sorry, this will be আমার এখানে একটা ভুল হয়ে গেছে, এটা P4 হবে, হ্যাঁ। Yeah, go on please. Okay, so what will happen in that case? R1, R2. Okay. So what do I have over here? Instead of M, how many rows do I have?
Yes, sir. Sir, 4 rows by as of now.
Yeah, if I drop one.
So then 3 rows.
How many linearly independent rows?
3.
Okay. So 3 rows which are linearly independent. And columns?
Yes.
Columns is that is also 3.
Yes,
okay,
sir.
so in that case, what is the problem? I'm getting a square into square. My rank is 3. It's square into square. I'm getting a square matrix.
Sir, I am trying to say, sir, for example, we are removing the first equation, that is 1, 2, 0. That we are removing that. Then we are getting one specific matrix, and if we remove 2, 4, 0, then we are getting a different matrix. So won't the result be changing for that?
See, what you're doing is, don't think of it in terms of matrix. Think of this as equations. If R1 is equal to, sorry, R2 is equal to 2R1, is R1 and R2 two different equations?
No, sir. Same equation.
So suppose, let me ask you a question. How many equations are there?
Sir, two equations are there in total.
Why?
So the first three are identical to each other. So that's why I told just two equations are there.
So here also, it's the same thing. What I've simply done is, I multiplied it by 2. Look at this. How many equations do I have?
So still two only. একই জিনিস তো।
একই জিনিস হচ্ছে।
আচ্ছা।
I'm simply trying to confuse you, you can say. I'm simply repeating the information in a slightly different way.
আচ্ছা আচ্ছা আচ্ছা। স্যার তার মানে স্যার একটা লাস্ট কোয়েশ্চেন এটা নিয়ে, তার মানে যখন আমি এই ক্যান্সেল করব তখন মানে আমি ইকুয়েশনের ফর্মে ভাববো, মানে জাস্ট ডিটারমিনেন্টের ফর্মে ভাববো না, তাই তো স্যার? ওকে স্যার, এটাই প্রশ্নটা ছিল। ঠিক আছে স্যার, থ্যাংক ইউ।
তুমি ডিটারমিনেন্ট তুমি কি এই ম্যাট্রিক্স, can you find out that wait a minute.
ও সরি ডিটারমিনেন্ট বলছি।
Can you find out the inverse of this matrix?
না
4
না না,
into 3 matrix.
আমি ভুল করে ডিটারমিনেন্ট বলেছি, মানে আমি বলতে চাই
Can you find out the can you find out the inverse of this matrix? 4 into 3 matrix.
No sir, not possible. We can't find
But if
the
this
inverse.
matrix is actually a 3 into 3 matrix, then can you find out the inverse?
Yes sir.
If you drop one equation?
Yes sir. One of the first two equations, if we drop, then certainly we can find the inverse of this one.
Now, if the first and second equations were really different from each other, then dropping them would not be valid. But you simply have the same equation repeated twice. And that is what you are dropping. Okay, that is what you are dropping. That is why it will not make a difference. You can, although you start off with a rectangular matrix, an over-identified system, because you have extra irrelevant information, you can reduce the dimensions of the matrix and make it singular. Okay.
Yes sir.
So after you have dropped out the irrelevant information, the repeated equations, okay, you end up with a square matrix, and none of the rows and none of the columns are linearly independent. In that case, A inverse will exist. And we know that if A inverse exists, it is always unique. Right? So basically what I require is, if I've got let us say k number of k number of variables, I simply have to have a situation when the rank of the matrix is k, is also k. Okay. K will automatically become a square matrix of order k into k. I drop out the extra rows or extra columns, and I end up with a square matrix which is linearly independent, and I can solve this to get A inverse. So the important issue over here is linear independence. Okay, I need to have a system which is linearly independent. Okay, so I think I'll stop at this point because after this I will have to shift to determinants. So what I've taught up till here is covered in Chiang's book. Chiang's, in fact, I'm teaching from Chiang, but this is I've completed chapter 4 of Chiang and Wainwright's book. After this, you have to go to chapter 5. Okay?
Okay, sir.
So, is there any questions? Okay, so I'm stopping.